Hello, this is Marc Farssac speaking. I am a telecommunications engineer doing mobile and IoT development, working on the software and hardware side of projects as needed. What I'm going to show you today belongs to the IoT temperature sensing project that I have been documenting over the last days and that you can find in my YouTube channel. Previously, I showed you a Bluetooth low-energy gateway, programmed in Java and running on Android Things device that detects the temperature of remote Bluetooth sensors, displays it on the LCDs, and pushes it to the cloud. Finally, it shows the temperature reading in real time on an Android app running on a mobile phone. Today, I will show you the initial stage of an additional module programmed in C and running on a Texas Instruments MC3220 microcontroller with a Texas Instruments real-time operating system. This module will read the temperature of remote sensors linked using a sub-1 Ghz MASH network. Stay tuned for the coming videos. Now, from this setup, we will focus on the red PCB, a launchpad for the Texas Instruments MC3220 MCU. The firmware that I have developed is already installed and running. What we have here in this stage is the reading of a temperature sensor that I am simulating using a varistor, wired to the analog input of the microcontroller, and later displaying the red value of an LED display directly on the LCD of this multimeter. This multimeter is connected to a pulse width modulated analog output, to which also this LED is connected. So, since our analog input is converted to a digital value, we will have to calibrate it. Also, the conversion from the digital value read will have to be adjusted so the pulse width modulation can reproduce the initial voltage. We'll look later to the graphics and related analysis to understand this better. The architecture is the following. We have a real-time operating system, a firmware running 2 threads, one for reading and one for writing, a callback for the calibration push button, this one here, and a general purpose input-output to turn on the calibration LED. Instead of the temperature sensor, we will use, as I said, a variable resistor and calibrate the readings. We will measure the voltage at the voltage in, the voltage here at the resistor. We'll measure the ADC, the converted value, using our integrated development environment. And finally, we will measure the voltage out for a given pulse width of this modulated output. Let's have a look at it and see what happens without calibration. So now, we have a certain value in this resistor, and this value belongs to an input of 2 volts 78. If we look now at what we have at the output, this is 2 volts 36. This is normal, because the input and the output don't have anything to do if they are not adjusted to match each other. So what we are going to do now is see how this value changes when we change the resistor. We have 3 volts 21 at the input, but we have 272 at the output. Changing the value of this resistor, we will have, for example, now a value of 178 at the input and a value of 153 at the output. Now I'm going to switch on the calibration, which I will later explain how I have done. So now the calibration is on, this LED is also on, and now we can see that at the input we have a voltage of 178, we have at the output a voltage of 177. If we change this value to whatever, now we have at the input 101 volts, whereas at the output we have 999 millivolts, which is pretty much adjusted. And so we can do for all values. When we have 0 volts at the input, we have 53 millivolts at the output, and so on. 35, 350 at the input, 334 at the output. So how have we done this? Let's have a look at the related graphics. What we can see here is that for a certain voltage input, we have a certain voltage output. We also have a certain analog to digital conversion reading. I have read this conversion using the debugger of my integrated development environment. So this is the value that our microprocessor is converting this input into. And this output is the one that I'm having using a certain width for the pulse width modulation. Now, only for plotting purposes, I'm using as a pulse width the same value that I have as the digital input, so digital analog to digital conversion. But they have nothing to do with each other. I mean, they are proportional, but they don't have to be equal. So that's why this voltage out is not like the voltage in, because of two reasons. The first one, because there are some errors introduced when doing this conversion, and the second one, because the pulse width modulation is still not adjusted. So errors of the conversion plus errors of the pulse width. This needs to be adjusted. Analog digital conversion needs to be calibrated. We can see this in these graphics. We can see anyway that all magnitudes are linear. So we have a certain slope with a certain offset. We can see that the voltage out in yellow becomes, it's more different than the voltage in when the voltage increases. So we can see basically that the error increases 0.5 volts here, 0.0 something when the voltage is very low. And we can represent all these curves, all these graphics using mathematics. And that's what we need to do, because what we want to do is we want to have a voltage out equivalent to the voltage in. So the first thing that we need to do is to calibrate this. This reading has errors, as I said. We need to calibrate it. We need to know this analog to digital conversion, it belongs to some voltage input. And then we need to adjust the pulse width. So in the first case, we have for a certain voltage input an analog to digital conversion output. In our x-axis, we have the voltage input. In our y-axis, we have the analog to digital converted value. But in the second stage, we have in the x-axis the analog to digital converted value, or the pulse width. Actually, it's the pulse width. And in the y-axis, we have the voltage out. So in both cases, we have a graph with a certain slope and a certain offset. And this is what we can use using mathematics to find the relation of the pulse width in relation to the analog to digital converted value. Now, using some mathematics, we know that one of these curves, it's linear one, has a certain slope and has a certain offset. If we use the values from the previous table, we can isolate, and we have that the analog to digital conversion is equivalent, it's proportional to the voltage in certain proportion, this slope here, plus one offset. Great. So now we have one of the graphics. And now, if we do the same analysis for the voltage out, we see that the voltage out is also proportional to some pulse width modulation pulse width, so the width of the pulse width modulation, and a certain offset as well. So again, using the readings, we can isolate, we can find the slope, and we can find the offset. Now, what we want is the voltage in is equal to the voltage out. Why we want this? Well, basically now we have a varistor here. But if we have an NTC, a resistor that changes with temperature, we need to know what is the voltage that is being read. And without doing this calibration, we will just know the analog to digital conversion. So we need to calibrate our hardware. And this is what we are doing here. So because we want a voltage out that is equal to the voltage in, we can summarize these two equations and make only one. And by doing this, we will come to the conclusion that our pulse width of our pulse width modulation, it's equal to the analog to digital conversion minus 91.4 divided by 0.827.